kagamath! Malaos ko po! Welcome to our 10th Power episode. I am Teacher Andrew, your soulmate. Allow me to guide you in learning the different concepts and skills in Mathematics 9. In the previous Mathathon, we learned that quadratic inequality in one variable is an inequality that contains a polynomial of degree 2 and can be expressed in one of the following standard forms where a, b, and c are real numbers and a is not equal to 0. Ax squared plus bx plus c is greater than 0. Ax squared plus bx plus c is less than 0. Ax squared plus bx plus c is less than or equal to 0. And ax squared plus bx plus c is greater than or equal to 0. You will see a set of quadratic inequalities that we must write in standard form. 1. Negative 2x squared is less than or equal to negative 8. The second one, 0.1x squared plus 2.3x is less than negative 4. And the third one, negative 3x minus 5 is less than or equal to 2x squared. Item number 1. The inequality, negative 2x squared is less than or equal to negative 8. Some of you might suggest that we increase both sides by 8. Yes, that is correct. Negative 2x squared plus 8 less than or equal to 0 is the standard form of this inequality. But we can also do the following. We may make the coefficient of x squared positive. Also, negative 2 and negative 8 are both even integers. Hence, we divide both sides of the inequality by negative 2. Hence, the inequality can now be written as x squared is greater than or equal to 4. Yes, you heard me right. The symbol has been changed from is less than or equal to is greater than or equal to. You know why? Because we divided both sides of the inequality by a negative number. Remember, whenever you multiply or divide an inequality by a negative number, you must flip the inequality sign. The next step is to decrease both sides by 4. And there, the standard form is achieved. So, negative 2x squared is less than or equal to negative 8 can also be written as x squared minus 4 greater than or equal to 0. Let's record this in the table. Item number 2. 0.1x squared plus 2.3x is less than negative 4. I could sense it. You are planning to increase both sides by 4, and that's right. And you must get that the standard form is 0.1x squared plus 2.3x plus 4 is less than 0. But if you are a little anxious that the coefficients of x squared and x are not integers, well, relief is here. We can multiply both sides of the inequality by 10, since 0.1 and 2.3 both have one decimal place. The resulting inequality is x squared plus 23x plus 40 is less than 0. And you might have raised one strand of your eyebrow why the symbol has not been changed. There is no need to do this since we multiplied by a positive number. Let's record the results in the table. So 2 down, 1 to go, kagamath. Let's do this. So item number 3, negative 3x minus 5 is less than or equal to 2x squared. Are we thinking of the same thing? And that is to decrease both sides by 2x squared. So what must we get then? Of course, negative 2x squared minus 3x minus 5 is less than or equal to 0. I already arranged the terms in descending powers. But if your cranium feels itchy because of the negative coefficient of x squared, say no more. We just have to divide both sides by negative 1. Yes, by negative 1 only, since negative 3 and negative 5 are not even. And you must remember that we need to change the symbol since we divide both sides by a negative number. Hence, the inequality can now be expressed as 2x squared plus 3x plus 5 is greater than or equal to 0. So let's update the table. Warm-up is done. We are now ready to take on more challenges. And since we are mathematician yan, we will survive solving word problems involving quadratic inequalities in one variable. Problem number 1. Kevin shot an arrow straight upward with a velocity of 96 meters per second from an altitude of 20 meters. After how many seconds will this arrow be more than 100 meters high? Use the position equation. S equals negative 16t squared plus v sub 0 times t plus s sub 0, where s is the altitude after t seconds, s sub 0 is the initial height, and b sub 0 is the initial velocity straight upward. What do we have to solve for? It is the value of the variable t, which is the amount of time in seconds that the arrow will take to reach an altitude higher than 100 meters. This altitude is the variable s. We express this given information as the inequality s is greater than 100. According to the position equation, s is equal to negative 16t squared plus b sub 0t plus s sub 0. We must express s in terms of t by substituting the values of v sub 0 and s sub 0 in this position equation. According to the problem, the initial velocity v sub 0 is equal to 96, while the initial height s sub 0 is 20. Hence, s must be equal to negative 16t squared plus 96t plus 20. So, we may rewrite the inequality s is greater than 100 as negative 16t squared plus 96t plus 20 is greater than 100. We should rewrite this inequality in standard form. So let's decrease both sides of the inequality by 100 in order to set it to 0. The resulting inequality is negative 16t squared plus 96t minus 80 is greater than 0. But if we want the numerical coefficient of t squared to be positive, and if we want to deal with smaller numbers, we must divide both sides of the inequality by negative 16. By a negative number because we want to make the coefficient of t squared positive, since negative divided by negative is positive. And why negative of 16? Simply because negative 16, 96, and negative 80 are all divisible by 16. And this will result to the inequality t squared minus 6t plus 5 is less than 0. Hence, we have to determine the set of values of t for which the polynomial t squared minus 6t plus 5 is less than 0 or negative. And the first thing we do is to solve the quadratic equation that corresponds to the given inequality. And I am referring to t squared minus 6t plus 5 equals 0. Observe that the symbol in the inequality is just changed to equal sign. The quadratic equation can be solved by factoring. Hence, we rewrite it as the binomial t minus 1 times the binomial t minus 5 equals 0. And equating each factor to 0, we can conclude that the values of t are 1 and 5. 1 and 5 are the roots of the equation and are also called the critical points that will serve as boundaries when we divide the number line later into regions or intervals. These values will make the polynomial and the inequality equal to 0. Remember, we are looking for values of the variable t for which the polynomial t squared minus 6t plus 5 is negative or less than 0. We may rewrite the inequality in a way that shows the factored form of the polynomial of degree 2. Now let's test 1 and 5 against the inequality to make this crystal clear. See the computation. Let's plot the critical points now on the number line. We will use hollow circles since these critical points are not part of the inequality's solution set. Then, we will draw a broken line through each of them to divide the number line into regions or intervals. Why broken lines? Again, it's because the critical points are not part of the solution set. But we Filipinos must always aim to be part of solution, mustn't we? The number line should look like this. Let's add the following details on the graph. At t equals 1, the value of the factor t minus 1 is 0. And at t equals 5, the value of the factor t minus 5 is 0. We must identify which among the regions in the number line contains the set of values of t for which the product of the two factors t minus 1 and t minus 5 is negative. Their values, then, must be of different signs. So we are looking at two cases here. Case 1, t minus 1 is less than 0 and t minus 5 is greater than 0. Case 2, t minus 1 is greater than 0 and t minus 5 is less than 0. In the region to the left of 1, we may use 0 as the test value. And when t is equal to 0, t minus 1 should be equal to 0 minus 1, and the result is negative 1. Hence, in this region where t is less than 1, the value of t minus 1 is negative. In the region between 1 and 5, we may use 3 as the test value. And when t is equal to 3, t minus 1 will be equal to 3 minus 1, or simply 2. Hence, in this region where 1 is less than t and t is less than 5, the value of t minus 1 is positive. In the region to the right of 5, we may use 9 as the test value. So when t is equal to 9, t minus 1 will be equal to 9 minus 1, or simply 8. Hence, in this region where t is greater than 5, the value of t minus 1 is also positive. Let's add these observations in the graph. Now let's use the same set of test values to determine the sign of the value of the factor t minus 5 at each interval. In the region to the left of 1, we may use 0 as the test value. So when t is equal to 0, t minus 5 will be equal to 0 minus 5, or negative 5. Hence, in this region where t is less than 1, the value of t minus 5 is negative. In the region between 1 and 5, we may use 3 as the test value. When t is equal to 3, t minus 5 is equal to 3 minus 5, and the result here is negative 2. Hence, in this region where 1 is less than t, but t is less than 5, the value of t minus 5 is also negative. In the region to the right of 5, we may use 9 as the test value. And when t is equal to 9, t minus 5 must be equal to 9 minus 5, or simply 4. Hence, in this region where t is greater than 5, the value of t minus 5 is positive. Let's add these observations in the graph. Look at the number line closely. Recall that we were looking at two cases to determine the solution set of the inequality. So, where on the graph do we see that the value of the factor t minus 1 is negative and that of the other factor t minus 5 is positive? Nowhere. Hence, the solution set for case 1 is an empty set. Where on the graph do we see that the value of the factor t minus 1 is positive and that of the other factor t minus 5 is negative? It is in the region where 1 is less than t and t is less than 5. Hence, the solution set for case 2 can be expressed by the same double inequality. 1 is less than t and t is less than 5. Written in interval notation, this inequality is expressed this way. It is an open interval. We use parentheses, since the boundaries 1 and 5, in this case, are not part of the solution set. Therefore, the solution set for the inequality t squared minus 6t plus 5 is less than 0 is the union of the solution set for case 1 and of the solution set for case 2, which is just equal to the solution set for case 2. Hence, the values of t for which the inequality holds true must be greater than 1 but less than 5. Let's plot this set on the number line. This means that after more than a second but less than 5 seconds, the arrow will reach an altitude that is higher than 100 meters. Let's solve another problem. Anna is instructed to make a garden plot which has an area less than 18 square feet. The length should be 3 feet longer than the width. So what are the possible dimensions of the garden plot? The garden plot is presumably rectangular. Its area is less than 18 square feet. Recall that the area of a rectangle is obtained by getting the product of its length and its width. Hence, we have the inequality A is less than 18 or L times W is less than 18. The length L must be 3 feet longer than the width W. So, L must be equal to W plus 3. And therefore, area will be expressed as the binomial W plus 3 times W. And in terms of the variable W, the inequality may now be written as the binomial W plus 3 times W is less than 18. The inequality must be written as W squared plus 3W is less than 18 after applying distributive property of multiplication on the left side. Then, we decrease both sides by 18. This will result to W squared plus 3W minus 18 is less than 0. And we have to determine the set of values of the variable W for which the value of the polynomial W squared plus 3W minus 18 is negative. Now that the inequality has been written in standard form, we can now start taking steps in solving it. First, we solve the quadratic equation W squared plus 3W minus 18 equals 0, which corresponds to the inequality, and it can be solved by factoring. Hence, the equation may be written as the binomial W plus 6 times the binomial W minus 3 equals 0. Equating each factor to 0, we can conclude that the values of W are -6 and 3. These are the critical points that will serve as boundaries in dividing the number line into regions or intervals. Also, the inequality may now be expressed as the binomial W plus 6 times the binomial w minus 3 is less than 0. Let's test the roots of the equation against this inequality. By substituting each of them in the inequality, we must be convinced that they are not part of the inequality's solution set. Now let's plot the critical points now on the number line. We will use hollow circles since these critical points are not part of the inequality solution set. Then, we will draw broken line through each of them to divide the number line into regions or intervals. Why broken lines? Again, it's because the critical points are not part of the solution set. Now let's add the following details on the graph. At w equals -6, the value of the factor w plus 6 is 0. At w equals 3, the value of the factor w minus 3 is 0. The inequality, binomial w plus 6 times binomial w minus 3 is less than 0, implies that the values of the factor must be of different signs. And we have two cases for this. Case 1, w plus 6 is less than 0 and w minus 3 is greater than 0. For case 2, w plus 6 is greater than 0 and w minus 3 is less than 0. So, we will use a test value to determine the sign of the value of each factor in each region or interval. In the region to the left of -6, we may use -7 as the test value. When w equals -7, w plus 6 will be equal to -7 plus 6, or simply -1. Hence, in this region where w is less than -6, the value of w plus 6 is negative. In the region between -6 and 3, we may use 1 as the test value. So when w is equal to 1, w plus 6 will be equal to 1 plus 6 and the result is +7. Hence, in this region where -6 is less than w and w is less than 3, the value of w plus 6 is positive. In the region to the right of 3, we may use 5 as the test value. And when w is 5, w plus 6 will be equal to 5 plus 6, in which the result is 11. Hence, in this region where w is greater than 3, the value of w plus 6 is also positive. Let's add these observations in the graph. And let's use the same set of test values to determine the sign of the value of the factor w minus 3 at each interval. In the region to the left of -6, we may use -7 as the test value. And when w is -7, w minus 3 will be equal to -7 minus 3, in which the result is -10. Hence, in this region, where w is less than -6, the value of w minus 3 is negative. In the region between -6 and 3, we may use 1 as the test value. When w is equal to 1, w minus 3 will be equal to 1 minus 3, in which the result is -2. Hence, in this region where -6 is less than w and w is less than 3, the value of w minus 3 is also negative. In the region to the right of 3, we may use 5 as the test value. And when w is 5, w minus 3 will be equal to 5 minus 3, in which the result is +2. Hence, in this region, where w is greater than 3, the value of w minus 3 is positive. Let's add these observations in the graph. Now, where on the graph do we see that the signs of the values of the two factors are different? Only in the region where -6 is less than w and w is less than 3. Hence, this will already be the solution set for the inequality w squared plus 3w minus 18 is less than 0. Written in interval notation, the solution can be expressed by the open interval containing the boundaries -6 and 3. However, not all values in the solution set can be accepted as answers to the problem. We are to identify the possible dimensions of the Gordon plot Anna is instructed to make. And since length is expressed in terms of the width that is represented by the variable w, w must be positive. Hence, in the solution set -6 is less than w and w is less than 3, the accepted set of values of w can be expressed by the inequality 0 is less than w and w is less than 3. Increasing all sides of the double inequality by 3, we shall obtain the range of values of the variable L, which represents the length of the Gordon plot. Hence, the length can be longer than 3 feet, but it must be shorter than 6 feet. Considering only the integer values of w, the table will show us the possible dimensions of the Gordon plot. Hence, the Gordon plot could be 1 foot by 4 feet or 2 feet by 5 feet. Thank you for tuning in, Kagamath. It has been my pleasure to be your guide in learning the different concepts and skills in Mathematics 9. I am Teacher Andrew, your soulmate. Bye!